So in this video, we're going to talk about expected value. So expected value is going to tie to the idea of mean or average. And with our distribution table where we have our random variable, so we're going to look at this example again with number of cups sold. So where we could have these different outputs, in terms of just averaging those, we would just add up and divide by how many there are, like we did before. And we'll even look at a comparison of these two ideas. But what happens in this section is what we add in are these probabilities. So giving this percent chance of seeing these outcomes. So like I was saying in the previous video of, even though we have this value of 30 that we want to average, we want to take into account that it only happens 5% of the time. And then with 60, we want to kind of weight that value because it has a higher percent chance of occurring. So with expected value, what we're really doing is taking what we would call a weighted mean or a weighted average, in that the probability is going to kind of provide weight to those things that have larger percent chance of occurring and weight things accordingly for things that have less chance of occurring. So let's look at a comparison of how what we usually did to take an average and how it's going to change in this section. So I'm just going to kind of cut this in half of what we did before, and then over on this right hand side I'll put what we want to do now, which is calculate expected value. Expected value for discrete random variables. So what we did before, and this will look a little bit strange, but I want to show you the background of it and kind of a breakdown of how we move from how we used to take averages to how we're going to take averages in this section. The key is that we have our data. So we have this 30, 36, 42, 48, and 60 for number of cups of coffee sold in a day. And if we just wanted to know the average or the mean, then what we would do is add them up and divide by how many there are, which there are 5 values. I'm just going to put the solution down a little bit because what I'm going to do is rearrange this formula so you can kind of see how we're going to move on to our next step a little more clearly. But this is going to come out to be a 43.2. So something we need to notice with this right off the bat is that we haven't taken into account the probabilities at all. This calculation of mean that we did before, it worked before because we didn't have these probabilities, but now we're just kind of ignoring this information by using that old form of the calculation. So something that happens when we take a mean is, in terms of weight, it's treating everything equally. And if I just rearrange this a little bit, the idea is that each piece is representing 1/5 here. By dividing by 5, using just kind of general rules of algebra, is that really this would be the same thing as writing 30 times 1/5 plus 36 times 1/5 plus 42 times 1/5 plus 48 times 1/5 plus 60 times 1/5. If I write it in this way, it's just a little more clear that each piece is representing 1/5 of the whole. So when we're averaging, this is what we're really doing. We have these data values, and then we're spreading them evenly to find out how they average. I'm even going to take this one step further and just change that 1/5 to a decimal, which would be 0.2, so that we could see how each piece is representing 20% of the whole. So if you plug in these 3 forms, this first one and second one and third one, if you plug in any of those into the calculator, you'll always get this 43.2 out. But what this is doing is it's treating it as kind of this even distribution of probabilities, which we don't actually have, which we don't have in these cases. We did before, but not anymore with expected value. So what we're doing is we're ignoring important information, and with that, our average is skewed and incorrect. So I know we just went through all of this work here, but we actually don't want to do this. If we have those probabilities available, we don't want to go through that. What we want to do is find expected value using that weighted average. The idea being, instead of treating it as an even distribution of the probabilities, we want to use the correct probabilities. So what I'm going to focus on is this form. Sorry, I know I just crossed it out, but this form right here where we can really see the percentages being evenly distributed. What we're going to do is change those percentages based on what's occurring in the table. So what we'll have is 30, and that's happening 5% of the time, plus 36, and that's happening 20% of the time, and 42, which is happening 25% of the time, 48 occurring 15% of the time, and 60 with 35% of the time. Now this calculation, it uses that form of how we could be calculating means, but adjusting the probabilities to match what we know based on our data. So if we plug that into the calculator, we should get a 47.4. So you can see a comparison of when we created the average before, that 43.2 is much lower. And it's that idea that it treated 30 evenly as 60, but now this 47.4, this moved higher up because it has these higher probabilities on this upper end. So it skews accordingly and weighting those larger values. So I would say is our wording would be similar to what we would do before. It's just our calculation has changed. So you could say the cafe can expect to sell, I'll go ahead and round this to a whole number, about 47 cups of coffee in a day. So with that, on a given day, they can expect to sell about 47 cups of coffee. So this form here is how we're going to be calculating expected value. And so expected value, which is just a form of a weighted mean. In terms of notation, we could write for expected value, and there's a few different forms. You might see E of X. This is just read as the expected value of X. You might also see the symbol for mean that comes up in statistics. It's the symbol mu that comes up in this when you deal with expected value. So those are interchangeable in terms of notation. You don't need to write out the notation at any point. It's just if they refer to those, it's referring to expected value. So what we're doing here in terms of a form and how we're doing this calculation, what we're doing is we're adding up across our data. So we're adding, and in terms of a general form, what we're taking each time is we're taking our X value and multiplying it by its probability. And so you're working across the table in kind of pairs. It's like, here's an X value and its probability, multiply them, plus, multiply, plus, multiply, plus, multiply, plus, multiply. So in terms of writing a formula, there's definitely a mathematical formula, but without getting too difficult with it, it's really thinking about our table of X and its probabilities and multiplying and adding those up. So what I'm going to say is to calculate, it's the sum of X times P of X for each X value. So the sum is telling us to add, and we're just going to add up this form of X times P of X. Some notation you might see, I'll just throw it in here. We haven't talked too much about this notation, but what you could see is something of this form, which has that same X times P of X piece. This idea of adding is coming through with this, this symbol sigma here is just telling you to add X times P of X, and then you just need to be sure to go across all of the data. but you can think of it in words as the sum of the x times p of x values. So this is how we find expected value. Once we have our table, you'll just take each data value times its probability and add them up as you go across the table.